LANL breakthrough. Quantum machine learning advances. A groundbreaking discovery has just changed the game for quantum computing. A team at Los Alamos National Laboratory has cracked a major puzzle in bridging classical machine learning with quantum systems. Their research, published in Nature Physics, proves that Gaussian processes, a cornerstone of classical AI, can now be harnessed for quantum machines, opening doors to entirely new possibilities. But here's where it gets controversial. Many experts once thought this was impossible due to the unique challenges of quantum computing. Let's break down why this matters and what it means for the future of technology. For decades, neural networks have powered everything from self-driving cars to language translation by mimicking human decision-making through layers of interconnected nodes. However, when scientists tried to replicate this success on quantum computers, they hit roadblocks. Quantum systems are so different from classical ones that even the most advanced neural network models struggled to adapt. This is where the LANL team stepped in, offering a radical new approach that sidesteps these hurdles. The key innovation lies in leveraging Gaussian processes, a statistical method that relies on probability distributions rather than adjustable parameters. Unlike neural networks, which require vast amounts of data and computational power to learn, Gaussian processes operate by assuming data follows a bell curve pattern. This makes them remarkably efficient, but also limited. For example, if the data doesn't naturally conform to a Gaussian shape, predictions can become unreliable. The LANL team solved this by developing advanced mathematical tools to verify their approach, ensuring accuracy even in complex quantum environments. This is the holy grail of Bayesian learning, says lead author Diego Garcia Martin. Imagine trying to predict house prices. You start with a basic assumption that values follow a bell curve. When you get a new data point, say a house priced at $500,000, the Gaussian process updates the curve to reflect this, refining the prediction. The more data you feed in, the better the result. Now the same principle could be applied to quantum systems, enabling more precise predictions for tasks like drug discovery or climate modeling. But this isn't just a theoretical breakthrough. The LANL team's work highlights a critical shift in strategy. For years, researchers have tried to force classical models onto quantum hardware, only to face issues like barren plateaus, mathematical dead ends that stall progress. Instead, the team advocates for building quantum machine learning from scratch, using principles that align with quantum mechanics. We need to find new ways of doing quantum machine learning, says lead scientist Marco Cerezo. Continuing to tweak old methods is like trying to fix a broken car by replacing just one part. We need a complete overhaul. This research isn't just about solving puzzles. It's about redefining what's possible. As quantum computers evolve, these techniques could unlock solutions to problems humanity hasn't even imagined. Yet, the question remains, will the quantum community embrace this paradigm shift? Or will they cling to familiar frameworks? What do you think? Let us know in the comments below. Quantum Machine Learning Explained. Speed-ups, challenges, and future of AI with quantum computers. Revolutionizing complex data processing. The promise and challenges of quantum machine learning. Imagine being able to process vast amounts of complex data exponentially faster than the most advanced computers today. Welcome to the world of quantum machine learning, QML, a rapidly evolving field that's poised to revolutionize data analysis by harnessing the power of quantum computation. But here's where it gets fascinating. QML is not just about speed. It's about tackling problems that are currently unsolvable with traditional machine learning methods. Researchers from the Center for High Energy Physics at the Indian Institute of Science, including Samarth Kashyap, Rohit K. Ramakrishnan, and Kumari Jyoti, alongside Apurva D. Patel and others, are exploring the theoretical foundations of QML. Their work systematically categorizes different approaches and critically evaluates recent developments, such as quantum-enhanced principal component analysis. This review highlights the potential for speed-ups in areas like materials science, but also acknowledges the significant hurdles posed by current quantum hardware, including noise and scalability. So what exactly is QML? Simply put, it's a field that leverages quantum algorithms to overcome the limitations of classical machine learning, particularly when dealing with complex and expansive datasets. While still in its early stages, QML demonstrates promise for accelerating certain computational tasks and potentially achieving results beyond the reach of conventional methods. However, there's a catch. Efficiently encoding classical data into quantum states is a central challenge in QML. Several encoding schemes have been proposed, each with its own trade-offs between circuit complexity and the number of qubits required. Amplitude encoding, for instance, offers a more compact representation, minimizing the number of qubits needed but demands complex quantum circuits for data preparation. Researchers are continually refining these and other encoding methods to optimize performance on near-term quantum hardware. Beyond encoding, a key focus is leveraging quantum data directly, data originating from quantum systems. This requires a shift in perspective, moving beyond the structures of classical machine learning, and is becoming increasingly relevant as quantum sensors and error correction techniques mature. Recent theoretical work has established a framework for quantum learning theory, extending classical concepts like sample complexity to the quantum realm. This allows researchers to rigorously analyze the potential benefits of QML algorithms. While initial results suggest that QML may not offer a dramatic advantage for all tasks, there are indications of potential polynomial speedups under specific conditions. But here's the part most people miss. The field is moving beyond simply replicating classical algorithms. Researchers are developing new quantum oracles, tools that allow algorithms to query data in a quantum manner, and exploring how these can be used to build more powerful learning models. However, the benefits of QML are not universal. Computational advantages are strongly dependent on the specific problem being addressed. So what's the path forward? A practical approach likely involves hybrid systems, where specialized quantum subroutines are integrated into larger classical computational workflows. Future research should focus on developing quantum algorithms specifically tailored to these hybrid systems, alongside improvements in error correction. Ultimately, the broader utility of QML will depend on overcoming technological limitations and identifying niche applications where its advantages outweigh its costs. But one thing is clear. QML has the potential to revolutionize complex data processing, and its possibilities are too great to ignore. Now, we'd love to hear from you. Do you think QML will live up to its promise? Will it revolutionize data analysis, or are its challenges too great to overcome? Share your thoughts in the comments below. Revolutionizing quantum machine learning. New insights from Lab. What if the future of quantum computing hinges on a mathematical concept that's been around for centuries? Researchers at Los Alamos National Laboratory have cracked a puzzle that's baffled the quantum community for years. How to adapt the power of neural networks for quantum computers without falling into the same tracks that plague classical systems. But here's where it gets tricky. This breakthrough isn't about copying existing models. It's about reimagining them entirely, using a tool called the Gaussian process. And this is the part most people overlook. The implications could reshape not just quantum machine learning, but our entire approach to solving problems that classical computers can't touch. For decades, neural networks have been the backbone of AI advancements, from self-driving cars to language translation. These systems mimic the human brain with layers of neurons that process information. But when scientists tried to force this same structure onto quantum computers, things went sideways. Quantum neural networks hit roadblocks like barren plateaus, mathematical dead ends where learning becomes impossible. Martin LaRocca, a quantum algorithms expert at LANL, puts it bluntly. We were trying to copy-paste classical models into a quantum world. It just didn't work. The LANL team, led by Marco Cerezo, took a different route. They asked, what if we abandon parametric models altogether? Enter the Gaussian process, a statistical tool that predicts outcomes based on probability distributions. Unlike neural networks, which tweak millions of parameters, Gaussian processes rely on a bell curve to model data. The team proved that these processes can be applied to quantum systems, opening the door to quantum machine learning that avoids those pesky barren plateaus. Diego Garcia Martin, the paper's first author, compares it to predicting housing prices. Start with a bell curve of prices. Add a data point, a house and its cost, and the curve updates itself. The more data you feed it, the sharper the prediction. Now imagine doing this with quantum data. But here's the kicker. This isn't just theory. The team's work, published in Nature Physics, mathematically proves that quantum neural networks can converge to Gaussian processes. That's a big deal. For starters, it means we can now perform Bayesian inference, updating predictions as new data arrives on quantum computers. And this is the part that could spark debate. Should we even be trying to adapt classical models for quantum systems? Cerezo argues we're chasing a dead end. We need to stop forcing square pegs into round holes, he says. Quantum computing demands a whole new toolbox. So what's next? The research is still in its infancy, but the LANL team is pushing for a paradigm shift. Instead of retrofitting old models, researchers should focus on quantum native methods. This isn't just about solving complex problems faster. It's about tackling problems that are currently impossible. Think drug discovery, climate modeling, or optimizing global supply chains. But will the quantum community embrace this radical approach? Or will they cling to familiar frameworks despite their limitations? We'd love to hear your thoughts. Do you think quantum machine learning needs a complete overhaul? Or can classical models be salvaged? Share your take in the comments below. Paper: Quantum Neural Networks Form Gaussian Processes. Nature Physics. DOI 10.1038-1457-025-02883Z. Funded by the Laboratory Directed Research and Development Program and the Center for Nonlinear Studies at LANL.